Welcome to Hartman Math. Before we get to verifying identities, let's do a little bit of review through our warm-up here of using fundamental identities, simplifying each expression. Pause the video here as you work through the problems. All right, number one, I think we got Pythagorean identities for both numerator and denominator. And then for cosine squared theta, it's in terms of cosine. Cotangent squared theta, we might want to get that in terms of sines and cosines. And remember, dividing by this would be the same thing as multiplying by its reciprocal. So cosine squared theta times the reciprocal of cotangent squared theta in terms of sines and cosines would be, well, the reciprocal of cotangent squared theta would be tangent squared theta, which we have here. And then we've got some factors that can cancel, so we're left with sine squared theta. Number two, we've got cofunction identity. Cofunctions of complements are equal. The cofunction to cotangent is tangent. Complement to pi over 2 minus x is x. So we're talking about tangent of x. And then again, maybe we go sines and cosines. So tangent of x by quotient identity would be sine x over cosine x. Factors cancel. We're left with sine of x. This is lesson 5.2, verifying trigonometric identities. We're going to tweak some of the guidelines and rules here just a little bit. Number one, it says to work on one side of the equation at a time. You can just get rid of that. Work on only one side. So pick one side to work on that. It is often better to work with the more complicated side. Not first, but totally. Because it's easier to simplify something than to take something simple and complicate it in the correct way. Look for opportunities to factor, add or subtract, square a binomial, create a monomial denominator, okay? Maybe using conjugate. Look for opportunities to use the fundamental identities. You can try getting in terms of sines and cosines only. And probably the most important one, always try something. Even if it doesn't get you there, it might give you an idea of what you might be able to try next. Example number one. So an identity is an equation like this that is always true, not true sometimes. So if we were to write like x plus 3 equals 7. That is not an identity because it's not always true. If x is 1, it's not true. So it has to be always true to be an identity. This is an equation that's always true, and we're going to try to prove it. So we're going to work on the more complicated side. That's going to be the left side here, clearly. So we've got a few things going on. We might recognize, well, I know that the squares, that could be a Pythagorean identity, and I know that cosecant squared and cotangent squared, those are the ones that go together as Pythagorean. So that's going to be Pythagorean, and that becomes 1. Okay. Keep in mind what our goal is here. So we could do reciprocals here. So flip them up. Reciprocal, reciprocal. And then in terms of cotangent squared, remember one of those guidelines, things we could try, is sines and cosines. So quotient identity or cotangent squared theta. Make sure we go all the way. We have to finish and match it to over here. So they do cancel out. We get cosine squared theta, check, as it is exactly what it is here. Checkpoint, go ahead and try this one. Work on one side until you get it to match the other. Pause here. I would choose to work on the left, and we're dealing with odd and even identities at the beginning. Secant is even, so this just becomes the secant of x, or secant of positive x. Cosecant is odd, so the negative is going to come out in front. It's the opposite of cosecant x. After that, we can do some reciprocals. Secant x on top becomes cosine of x on the bottom. Cosecant of x on the bottom, reciprocal becomes sine of x on the top. The negative can go out in front, quotient identity, and it matches. Example number 2, verify. Okay. I'm going to choose the left side to work on. Addition in terms of fractions is definitely more complicated than multiplication. So I'm going to choose to work on the more complicated side. And to get us started, I don't see an identity to go with, so I'm going to just do this. Let's go ahead and add them. So we're going to need a common denominator. We're going to need both of these. So the product of secant y minus 1 and secant y plus 1 is our LCD. This one's missing secant y plus 1, multiply top and bottom. This one's missing secant y minus 1, multiply top and bottom. And we're going to add it all together. So now if we do a little simplifying, we're going to get secant y plus secant y is 2 secant y. That's at least we get the 2 part of that, so we're heading there somewhere. The plus 1, the negative 1 cancel out, and then we can multiply these together, secant squared y minus 1. And that's going to be a Pythagorean identity. And I know that secant squared y is going to be related to tangent squared y. So if I look at my identities, that's going to become tangent squared y. So we might want to try the strategy of sines and cosines, in which case, here with secant y, we could send that to the bottom as reciprocal, cosine y on the bottom. And then the tangent squared y, we are trying to get to cotangent y. So if we did reciprocal there and also did sines and cosines, it would come up as cotangent. We could do that in terms of sines and cosines, cosine over sine. So here's our cotangent squared written in terms of cosines and sines. And then we can have one of the cosine y's cancel out, in which case we would be left with 2, a cosine y, and if we split the sine squared y to be sine y times the sine of y, then we're almost there. 2, that's going to be cotangent y, that's going to be cosecant y. Make sure we finish it, and that one's done. Checkpoint, pause the video here, work through, verify the identity. And I think we want to begin by factoring. We have a common factor of, now in terms of the sine x's, we would want to take the sine x that's raised to the lower power. That would be sine 1/2 x is a greatest common factor. Cosine x itself is a greatest common factor. We're going to factor that out. Keep in mind that when we factor out sine to the 1/2 x here, remember the rule is that when we figure out what's left over, what will we multiply by, the rule with exponents is that you would add the exponent. So we're wondering, as we factor out sine to the 1/2 x, 1/2 plus what is 5/2? And that would be 2, or 4/2. That's why that's coming up there. And then, well, if we can rewrite from exponential notation into radical notation, that means the square root of sine x. And that one there, that's Pythagorean. And multiplying those together, we get cosine cubed x. Example number 3. Not exactly clear which one we want to work on, so you could kind of work on one. But I think this is the one that I want to choose to work on, where we have definitely some differences in denominator. So the idea of conjugate might be a way to go. So usually it's about the denominator, so we're going to multiply top and bottom by the conjugate of the denominator. So I don't really want to do anything to there because I think those are pretty close. So that's where we'll start. We're going to left and multiply by the conjugate inside the root top and bottom. So in which case, 1 plus sine theta times 1 plus sine theta is 1 plus sine theta, the quantity squared, and then this is a difference of squares. And then Pythagorean identity right there, 1 minus sine squared theta is cosine squared theta. Now we should be able to take the square root. Square root here, we get 1 plus sine theta. Square root here, we get the absolute value of the cosine of theta. The question I want you to think about, if I pause here, just think about it for a moment. Why did we need absolute value on the cosine theta? We didn't need it here on the 1 plus sine theta. Pause here, think about it. Well, the reason that we need absolute value on the cosine theta is because we're taking the square root of something and the result has to be positive. Cosine theta is not guaranteed to be positive. It's not positive in quadrant 2 or quadrant 3. So that's why it needs absolute value, to ensure that you get a positive response. Why isn't that the case in the numerator? Well, 1 plus sine theta, if we think of sine theta itself, sine theta, in terms of the graph, the lowest that it can be is -1. And when we add 1 to that, it's not going to be negative. It can't be negative. And that's why we don't need an absolute value on that one, because the 1 plus sine theta can't be negative anyways. So if it's guaranteed to be positive, we don't need the bars. Example number 4, converting to sines and cosines. Here we go. We're going to work on the left side again. In terms of this way subtraction, it's a little bit more challenging. So if we go sines and cosines, then we're going to use reciprocal identity on secant x. And then let's go ahead and subtract these two. We need a common denominator, which will be cosine x. So I'll multiply top and bottom by cosine x. The numerator is Pythagorean identity. That's sine squared x. And we can split that up to be 1 sine of x times another sine of x over cosine of x. So we've got a sine of x and then the sine x over cosine x. That's our tangent of x. Example number 5. Which side do we want to work on? I think that the right side's probably definitely the more complicated, so let's work there. And there's different ways to go. We could go sines and cosines. The challenge with that would be we're going to create complex fractions, so fractions within fractions. And maybe we do that anyway, but I think maybe we might want to try first conjugate. So now, if we multiply the bottom, we get secant squared beta minus tangent squared beta. I think that's going to be 1. So now we're just dealing with this. And cotangent beta times tangent beta, they're reciprocals. And when you multiply it by reciprocals, you get 1. So just the challenge is, what is cotangent beta times secant of beta? Now might be the time to go sines and cosines. But I know for the second one, that one we can do cotangent beta times tangent beta. They're reciprocals. So we have to get the 1 there. So our cotangent beta, quotient identity, secant beta, reciprocal identity, plus the one that we were talking about. Now the cosine betas are going to cancel. We get 1 over sine beta plus 1. And reciprocal identity, we're going to get cosecant beta plus 1. There it is. That's it for today. I'll see you next time.